Hello friends, George here. Welcome to the channel. Today we are exploring some fascinating graphical curves called Lissajous curves in BASIC on a Commander X16 emulator. We will draw the curves, look at the 15 lines of BASIC code and try to understand it by building it up from scratch again. Before we start, I have to give credit to Armando Pavese from the Auric One and Atmos Facebook group who inspired me to make this video. Armando, love your work. So, what are these beautiful curves? Lissajous curves are a family of figures that reveal the beauty of harmonic motion. Named after the French physicist Jules-Antoine Lissajous, these curves are the graphical representation of two oscillations perpendicular to each other, each with their own frequency. Imagine two waves, one moving horizontally and the other vertically. As they intersect, they create a dance of points that we see as Lissajous curves. These patterns are not just pretty to look at, they also hold significance in various fields from engineering to art. The shape of a Lissajous curve is determined by the ratio of the frequencies of these oscillations. When the frequencies are in a simple ratio, the curve will be closed and still, but when they are not, the curve appears to be in constant motion, never repeating the same path. So, let's dive in and discover the mesmerizing world of Lissajous curves, where mathematics meets art. After this small intro, let's go quickly through the code to get a rough overview. The code draws 12 Lissajous curves, which are carefully placed in a 4x3 table. Every curve has a different frequency, ratio and color. The basic functions for the coordinates are x equals sinus of a times t plus t plus 1, y equals sinus of b times t plus t. The basic idea here is to have two oscillations which are out of phase. I show you later why. Line 10 to 12. The rem statement is just defining a remark for the source code. Everything after rem is ignored. I use rem here to put a header over the actual source code. Line 15. CLS clears the text screen. On the Commander X16, text and graphics screen are shown at the same time. With screen $80, we initialize a graphics screen of 320 by 240 resolution. The color command defines the foreground and the background color. 5 stands for green and 0 stands for black. GOSUB jumps to line 99 and comes back when a return command is executed. In line 99 we draw 240 horizontal black lines to get an empty black screen. Line 20. The variable C stands for the foreground color. 1 stands for red because our first curve will be red. The x and the y are set to 35, which are the half of the maximum height and width of our figures. We also define pi for later use. Line 25 and 30. We set up two nested for loops. A iterates from 1 to 4 because our table has 4 columns, and B iterates from 1 to 3 because our table has 3 rows. Line 35. At the start of each curve we change the color by setting the color to C. After that we increase C by 1. Line 40. The third loop, which iterates over t. T starts from 0 and goes up to 2 times pi, which is the circumreference of a circle with a radius 1. We also iterate in 0.02 steps. Line 45 and 50. Here we calculate the x, y coordinates of each point for every Lissajous shape. A, B and T are changed in every iteration within 3 nested for loops. Line 55. Every shape starts with t equals 0. Then we draw our first point and save the values x and y to xs and ys. S stands for save, so that we can draw a line in the following iteration to the previous point to get a nice line. Line 60. We draw here the line, and the line starts at point xs, ys and ends at x and y. Line 65. Next t, b, a is equal to next t, next b, next a. Next t increases t by 0.02. Jumps to line 45 until it reaches 2 times pi. Next B jumps to line 35 until B reaches 3, and next A jumps to line 30 until A reaches 4. Line 70. Get A string, reads the current pressed key and puts the value in the variable A string. The $sign indicates that the variable A string is a string. If no key is pressed, A string equals an empty string, and therefore it jumps at the beginning of the same line 70. So we have an endless loop until we press a key. Line 75. If a key is pressed, we clear the graphics screen by jumping to line 99 again and come back. We set the color to 5, which is green, and clear also the text screen with CLS to get the cursor at the upper left. And at last we list our program and end the program, so line 99 is not executed again. So let us build up the code, and I want to show how this works here. First of all, we will reduce the for loops from 1 to 1 so that we draw only one figure. And then I will go not from 2 pi but to pi. And we leave the steps here. And I will reduce the equations here to dx and dy. So, like this. So let us press return and run the program, and we will get a point that was expected. So now we want to expand the point to an ellipse. So we add here the sinuses. So our formula here from here, t times t plus 1. And same here with dx, sinus b times t plus t. So that should give us an ellipse. Let us try out. Okay, it gives us an ellipse, but the ellipse is too small because it has only the radius of 1. So we have to multiply it with a number. And because dx has the value of the half width and height of our figures, we have to multiply it with dx and dy. So dy, come on. So let us see what we get. Yep, a bug here. So where's the bug? dy. Okay, I have forgotten. And we get a nice ellipse here. So the ellipse is a little too big, and we multiply it with a value smaller than 1. Let's see, a 3/4 of it is okay. And we get a nice sized ellipse. So our next step is we want to position the ellipses here. So I will change this to A so that we get always an ellipse. So, and I will multiply it. So the first idea that comes to mind is, well, why don't we want the 4x3 table? So let us put this to 4 and this to 3, and then multiply dx with a and b, dx with a and dy with b. Let's try this out and see what we get. Okay, so times a, and this is times times b. So let us see what happens. So first is okay, second, oh, it overlaps. Okay, why does it overlap? Because the x is the half width of our table cell. Okay, so let the next idea is take it 2 times. So let us so 2a two times a and let's say 2 times b. Times b. So let's see what happens. Okay. So now we get a equally spaced table of circles, but the position is not right. Okay, let us go this through. Okay, so the next idea is if I do 2 times of a, well, when a is 1, then I have 2a, 2 times of dx. But when I have 2, I don't want 2, I want 1. So subtract 1. And here too. So that I get the table a little up and a little to the left. So let us see what happens. Okay, this looks nice. Better. So as you might notice, the table isn't centered properly. You can see it at the bottom, and left and right is the same. So we have to put it a little down and to the right. So we just add some numbers. Nothing easier than this. So we add just here 15. I do it at the end. Here 15 too. So this is just try and error. I figured it out. And okay, so we get the circles, and we don't want the circles, we want our figures. So we do the B here again. So let's run. The first is our circle. Second is our figure. Oh, it looks nice. Oh, we are missing something. The first and the first line and second column. here too. Okay, what's wrong here? We will see the code. I can tell you immediately. Well, we restricted here to pi, and we have to put here 2 pi. So 2 pi. Oops, 2 times pi. And that should be our end result. That's the steps how you get to the code, to a definite code here. Let's run it again. And we should get the nice curves from the original example. And friends, I think that's it for today. I thank you very much for watching. I hope you liked the video and enjoyed watching it. I really liked and enjoyed doing it. Have a nice day or evening depending where you are, and I hopefully see you in the next one. Bye bye.